With respect to trading costs, liquidity is least likely to impact the stock price, the bid-ask spreads, or the brokerage commissions. Well, if it's $7.99 a trade, it doesn't matter what liquidity is, it's $7.99 a trade, right? Brokerage commissions. Evidence of risk aversion is best illustrated by a risk-return relationship that is A, negative, B, neutral, or C, positive, a risk-return relationship. Well, if I want more return, there's more risk. More return, more risk. So that is a positive relationship. C, positive relationship. With respect to risk-averse investors, a risk-free asset will generate a numerical utility that is the same for all individuals, positive for risk-averse investors, or equal to 0 for risk-seeking investors. Will generate a numerical utility. Remember, utility is equal to the expected return minus 1/2 A times the variance. And it is saying with respect to a risk-free asset. Well, the risk-free asset, the variance of the returns on the risk-free asset will be 0, which means this whole term goes to 0, so the utility will be the expected return on the asset. So it's saying we'll generate a numerical utility that is the same for all individuals. Yeah, because it just equals the expected return of the asset. That's it. So there we go. It will generate a numerical utility that is exactly the same. Here it's saying positive for risk-averse investors. Well, there's no guarantee your return is going to be positive. None at all. It's just an expected return, right? And equal to 0 for risk-seeking investors. Again, there's no guarantee that your return is going to be equal to 0. It is the same for all individuals. With respect to utility theory, the most risk-averse investor will have an indifference curve with the most convexity, the smallest intercept slope, or the greatest slope coefficient. So let's think about that now. You have multiple capital allocation lines, right? And if you have a risk-averse investor, you keep going up on your indifference curves until you get to the highest one, and the highest one has the highest slope. So with respect to utility theory, the most risk-averse investor will have an indifference curve with the greatest slope coefficient. They'll go as high as they can. Reason is they're very, very risk-averse, which means to get them to take even the slightest bit of risk, you must compensate them with significant amounts of return. So that's why you'd want the capital allocation line with where the indifference curve is just tangent to the highest capital allocation line. With respect to an investor's utility function expressed as follows, which of the following values for the measure of risk aversion has the least amount of risk aversion? Remember, the higher A is, the more risk averse it is, the lower it is, the least amount it has. So what's the lowest number here? -4, 0, or 4? I think that was an easy one, right? -4. A financial planner has created the following data to illustrate the application of utility theory to portfolio selection. 20. A risk-neutral investor is most likely to choose. Remember now, if we're risk-neutral, we simply maximize return. We just maximize return. So we're most likely to choose, highest return is 20%. That's investment 3. We're most likely to choose investment number 3. We're looking at the same data here. If an investor's utility function expressed as follows, and the measure for risk aversion has a value of -2. The risk-seeking investor is most likely to choose. Well, we have -2, so they're going to look for the highest risk. They're risk-seeking. Where is our highest risk here? Our highest risk, higher standard deviation is investment number 4. They're most likely to choose investment number 4, 2, 3. There it is right there, investment number 4. If an investor's utility function is expressed as follows, and the measure for risk aversion has a value of 2, the risk-averse investor is most likely to choose. Well, here we got to do a little bit of math. We're going to have to do some math on this one. So let's look at what we have here. I'm going to write it up here instead of, I don't want to crowd the bottom of the screen. So our returns are 0.18, 0.19, 0.20, and 0.18. We're just using this function here. I just put out the first term. Minus, and of course we have 1/2 of A, Our A is 2, so 1/2 of A is 1. So I'll just drop off the 1. And it's the variance of the asset. This is expected standard deviation, so it'll be 0.02 squared. Next one is 0.08 squared. This is 0.15 squared. This is 0.3 squared. Again, I just want to be clear that even if I put in the 1/2 A is 2. 1/2 of 2 is 1. This would simplify to 1 anyways. There's no point in putting it in. So if you multiply this out, we'll get 0.1796. This multiplied out is 0.1836. This will give us 0.1775, and this will give us 0.09. And we want to maximize utility, so let's look for the highest number, 0.1836. That comes from the second portfolio. This is investment number 2. This was 1, 2, 3, 4, recall. Number 2, so do we have that choice here? Investment 2. All right, the same information here. If an investor's utility function is expressed as follows, and the measure for risk aversion is a value of 4, the risk-averse investor is most likely to choose. We'll do the same thing. Investor 1, 2, 3, 4. We have 0.18, 0.19, 0.20, 0.18 minus, and we have 1/2 of A. Here A is 4, so 1/2 of A is 2. So it's 2 times, and the variance. And this is standard deviation, so 0.02 squared. The next one is 0.08 squared. Next we have 0.15 squared. And here we have 0.3 squared. And we just simply solve each one. We'll get 0.1792, 0.1772, 0.1550, and nothing. So we just choose the highest one, and we have 0.1792. That's investment number 1. Investment number 1, child's play. With respect to the mean variance portfolio theory, the capital allocation line, CAL, is the combination of the risk-free asset and a portfolio of all risky assets, equity securities, or feasible investments. Remember we said risky assets only, right? Risky assets. Two individual investors with different levels of risk aversion will have optimal portfolios that are below the capital allocation line, on the capital allocation line, or above the capital allocation line. Well, you wouldn't be below because you could do better by moving up to the capital allocation line. You wouldn't be above because they're unattainable. They would both be on the capital allocation line. With respect to the capital market, with respect to capital market theory, not the capital market theory, but with respect to capital market theory, which of the following asset characteristics is least likely to impact the variance of an investor's equally weighted portfolio? Least likely to impact the variance. The return on the asset, the standard deviation of the asset, or covariances of the asset with other assets in the portfolio. Well, least likely to impact the variance, the standard deviation of the asset will, so we can eliminate that. Covariances of the asset with the others in the portfolio will, they're additive to the portfolio variance, right? So that will, the return on the asset. And in fact, the return on the asset does nothing to impact the variance on an equally weighted, well, on any portfolio. When you look at the way we calculate the variance, it's a weighted. We weight the returns of the individual assets. Nowhere in that calculation do we use variance, standard deviation, or covariance at all. A portfolio manager creates the following portfolio. We have 2 securities, weighted 30% and 70%, and their expected standard deviations. If the correlation of returns between the 2 securities is 0.4, so I'm given correlation, the expected standard deviation of the portfolio is closest to. I'm being asked for the expected standard deviation, but we know that we can calculate the variance of the portfolio, so let's do that, and then we will just take the square root. Remember, we have one step. So what do we do here? The weighting of the first asset, 0.3 squared times the variance of the first asset. We're given standard deviation, so let's remember to square it to get variance, plus the weighting on the second asset, squared, plus the standard deviation on that asset, squared for variance, plus 2 times the weighting on the first asset, times the weighting on the second asset, times the correlation times the standard deviation on the first times the standard deviation on the second. So these are variances, these are standard deviations at this end. This point is just calculator work. This first term will settle out to 0036 plus this will settle out to 00756, and all of this will settle out to 0.004032. Add it all together and we will get 0.014688. Let me make sure I got a 0 in there. Now that's the variance. We want the standard deviation, so you got to take a square root of that, and we will get 0.12119 or 12.12. 12.12. There's a 12.1. I'll take it. A portfolio manager creates the following portfolio. It's the same setup we have above. If the covariance of returns, now we're given a covariance, between the two securities is negative 0.024, the expected standard deviation of the portfolio is closest to. So we'll calculate the variance of the portfolio again. The first two terms will stay the same, so let's just copy what we have, 0.007056. Let me get my zeros straight because I don't want to cause confusion. Plus, this will be 2 times the weighting on the first asset times the weighting on the second asset times the covariance, 0, 2, 4. And this term will be a negative 0.01008. So if we add these two and subtract that, we'll get 0.000576. We want to take a square root of that. That'll give us 0.024 or 2.4%. Do I have that anywhere? I certainly do. So when you're reading these questions, let's make sure, again, underline what's being asked. This is giving you correlation and it's asking for standard deviation. This is giving you covariance and asking for standard deviation. Make sure you know what's given to you so you know which form of the formula you're using. Make sure what you're being asked so you know that you carry at that final step and take the square root instead of getting to 0.014, looking at the answers and getting frustrated going, oh, come on. And then recalculating until you realize, oh, hang on, I got to take it one more step. That will cause you a lot of frustration. All right, a portfolio manager creates the following portfolio. Notice we have the same information again. 9, if the standard deviation of the portfolio is 14.4, the correlation between the two securities is equal to. So we have the standard deviation of the portfolio. We need the we got to come up with the correlation between the two securities. So if we take 0.144, which is the standard deviation, and square it, we will get the variance of the portfolio, which will be 0.020736, and we know that it is equal to 0.0036, that was the first term, plus 0.007056, plus we had 2 times the weighting on the first asset times the weighting on the second asset. And here we're just going to let this equal x. X is the covariance between the two. Once we have the covariance, we can find the correlation, right? So all we have to do is just solve for x in this case, and x will equal 0.024. So I just took these terms, multiplied this out, subtract them from here, and divided by that term. Maybe I should have shown some intermediate steps in between. I would have gotten 0.01008 over 0.42, which would have given me 0.024 for x. X equals. So I know that my correlation 1, 2, I multiply by the standard deviation of the first asset, standard deviation of the second asset. That's covariance. And I know that it has to equal 0.24. So 0.024 must equal rho 1, 2, 0.2 times 0.12. And if you multiply 0.2 times 0.12, you'll get 0.024. So 0.024 must equal something times 0.024. This 1, 2 must equal 1. Do we have a 1? We do. Now, I'm not going through every step and stepping through it because I know your time is precious and you can do the calculator work. I'm just sort of trying to hit process here, right? If the standard deviation of the portfolio is 14.4%, which we just did, the covariance between the two securities is, well, we started by calculating the covariance and then we solved for the correlation. So we were doing the same step. The covariance is 0.024. There it is right there, B. So, done. Let's see, a portfolio manager creates the following portfolio: security 1 and 2, expected returns, expected standard deviations. If the portfolio of the two securities has an expected return of 15%, the proportion invested in security 1 is. So we know expected return of a portfolio is simply just the weighting on the first times the return on the first plus the weighting on the second times the return on the second, and we can write this in terms of 1 minus W1 and solve for W1, right? So the expected return on the portfolio is 0.15 would equal W1 times 0.16 plus 1 minus W1, 0.12. And if we expand this out in here, we'll get 0.16 W1 plus 0.12 minus 0.12 W1 is equal to 0.15. 0.16 W1 minus 0.12 W1 is 0.04 W1 plus 0.12, and this 0.15. Bring that over to the other side. We'll have 0.03 is equal to 0.04 W1. That means W1 must equal 0.03 over 0.04, which is 0.75. Or 75%. W1 must be 75%. We got it. And you could check to make sure that's right. 75% of 16% is 12%. And 25% of 12% is 3%. So the 12 and the 3 would add up to 15. There's your 15. If the correlation of returns between the two securities is negative 0.15, and that's the two securities on the previous screen. I didn't rewrite them out, but the standard deviation of the first one was 20%. The standard deviation of the second asset was also 20%. The return on the first asset was 16%. The return on the asset on the second was 12%. If the correlation of returns between two securities is negative 0.15, the expected standard deviation of an equal weighted portfolio is closest to. So we need portfolio standard deviation. We always start by calculating the variance of the portfolio, and from there we just take the square root. So the variance of the portfolio is the weighting on the first asset. We're told they're equally weighted, so it'll be 0.5. The weighting on the first asset squared times the variance of the first asset is 0.2 squared, because that's standard deviation. Plus the weighting on the second asset, 0.5 squared, times the standard deviation of that squared for variance, plus 2 times the weighting on the first asset, weighting on the second asset, the correlation between the two, negative 0.15, times the standard deviation of the first asset times the standard deviation of the second asset. I think you can see from here on in that's really just calculator work, equals 0.01 plus 0.01, and we'll have a negative in here, 0.003, and that'll give us 0.017, but keep in mind that's the variance of the portfolio. We want the standard deviation of the portfolio, which means we take the square root, and we will get 0.13038. 13 and change, 1304. A. If two securities are uncorrelated, which means two securities are uncorrelated, the two we just did. If the two are uncorrelated, that equals 0. The expected standard deviation of an equal weighted portfolio is closest to. So if they're uncorrelated, this whole second term goes to 0, because this term will drop to 0. So it'll be the first term and the second term, which is 0.01 plus 0.01. So the variance of the portfolio will be 0.02. If we take the square root of the variance of the portfolio, we will get 0.1414, on and on and on, 14.14, 14.14. The analyst constructs two asset portfolios that are equally weighted. Which pair of assets has the lowest expected standard deviation? Well, we can see that we all have the same expected return on each one. And and we're looking at an equally weighted pair of assets. So what's going to matter here is the correlation between the two assets. So we want the combination of assets 1 and 2, 1 and 3, or 2 and 3, which offers the lowest correlation. Correlations, we know, go from -1 all the way to +1, and we already said that asset 2 and 3 are perfectly negatively correlated. You can't get lower than -1. -1, remember our last term is plus 2 W1 W2, the correlation between 1 and 2, and the standard deviation of both. The lowest this can get is -1, and if this is -1, this third term will not be additive. We'll subtract it. It'll actually significantly lower portfolio standard deviation or expected standard deviation. So we want two assets that are perfectly negatively correlated. We already said 2 and 3 are. So on 33, still sticking with asset 2 and asset 3. If the analyst constructs two asset portfolios that are equally weighted, which pair of assets provides the least amount of risk reduction? Well, we know 2 and 3 are perfectly negatively correlated. So we don't have to figure out 2 and 3. So it's between 1 and 2 and 1 and 3. And we know that the expected return is 6% in all cases. So you can eyeball this and say, well, 1 and 2 is 12 and 12, 0, 6, 6 and 0. Versus 12 and 0, 0 and 6, 6 and 12. 1 and 3 share no points. 1 and 2 share points. They probably have a higher correlation. I'll eyeball it and say asset 1 and asset 2. But if you want to do it just a little bit better, remember the covariance is the return on one minus its expected return multiplied by the return on the second one minus its expected return. We can do this quickly. 12 minus, we'll just do the covariance between 1 and 2. 12 minus 6 is 6 times 12 minus 6 is 6. So we'll have 36 plus 0 minus 6 is -6. 6 minus 6 is 0. 6 minus 6 is 0, well, plus 0, so we'll have a covariance of 36. Let's do it between 1 and 3. 12 minus 6 is 6, times 0 minus 6 is -6. 6 times -6 is -36, plus, well, if it's 6 minus 6 will be 0, so 0 times anything will be 0, plus, here 6 minus 6 will be 0, so 0 times anything is 0, that's -36. So the highest covariance belongs to 1 and 2. We know that 2 and 3 are perfectly negatively correlated, so that's why we don't have to worry about 2 and 3. So 1 and 2 has a covariance of 36. 1 and 3 has a covariance of -36, so there's a negative covariance between them that would lower portfolio risk. So the least amount of risk reduction comes over here, and this was from asset 1 and 2. Asset 1 and 2. As the number of assets in an equally weighted portfolio increases, the contribution of each individual asset's variance to the volatility of the portfolio increases, decreases, or remains the same. Well, I drew this out for you. This is number of securities. This is systematic risk. And we have diversifiable or non-systematic risk. And as we increase the number of securities, what happens is, as we increase the first few, you have big reductions in volatility of the portfolio, but as the number of securities increases, each incremental one is affecting the volatility of the portfolio less and less and less. So the contribution of each individual asset's variance to the volatility of the portfolio decreases. With respect to an equally weighted portfolio made up of a large number of assets, which of the following contributes the most to the volatility of the portfolio? Average variance of the individual assets, the standard deviation of the individual assets. We can see that this is saying the same thing, really. Average covariance between all pairs of assets. Well, if you think about it for a minute now, if you have, let's say, 10 assets, you will have 10 variances, but how many covariances will you have? You will have 10 times 11 over 2, that's 110 over 2 is 55 covariances. Which is the bigger number? Which do you think contributes more? Look at that. It's the covariance between all pairs of assets. The correlation between assets in a two-asset portfolio increases during a market decline. If there is no change in the proportion of each asset held in the portfolio or the expected standard deviation of the individual assets, the volatility of the portfolio is most likely 2. Well, what's going on between the correlations? The correlations, it says here, the correlations increases, and it's saying there's no change in anything else, no change in the weightings, no change in the standard deviations. Remember the last term, right? 2 times W1, W2. The correlation between asset 1 and 2, variance, standard deviation of 1, standard deviation of 2. It's saying that W1 and W2 are not changing, and these two items are not changing. And this is an additive term. If this increases, this whole third term gets bigger. And if it gets bigger, what's it going to do? Increase. So 31 is A. Which of the following statements is least accurate? The efficient frontier is the set of all attainable risky assets with the highest expected return for a given level of risk. All right. Lowest amount of risk for a given level of return. All right. So I'm okay with those two, so I'll take C because I'm looking for least accurate. Let's just find out. Highest expected return relative to the risk-free rate. No, that's not what the efficient frontier is at all. Remember now. What are we looking at here? The efficient frontier is from this minimum variance portfolio, the global minimum variance portfolio onwards, right? And it shows groupings of return for risk. The highest expected return for a given level of risk, that's what this will show. The lowest amount of risk for a given level of return, that's exactly what that'll show. The highest expected return relative to the risk-free rate, no, the risk-free rate is over here. Remember, we draw our capital allocation line. C, there you go. The portfolio on the minimum variance frontier with the lowest standard deviation, is unattainable. Well, it's saying it's on the minimum variance frontier, so it can't be unattainable. You can eliminate that. Is the optimal risky portfolio or the global minimum variance portfolio? It is the global minimum variance portfolio. Well, what's the optimal risky portfolio? Well, you draw your... There you go, where the capital allocation line is tangent to the efficient frontier. The set of portfolios on the minimum variance frontier that dominates all set of portfolios below the global minimum variance portfolio is the capital allocation line, Markowitz efficient frontier, or set of optimal risky portfolios. So let's make sure we know what we're being asked. It's saying the set of portfolios on the minimum variance frontier that dominates all sets of portfolios below the global minimum variance portfolio. So let's draw it out. If that's the global minimum variance portfolio, it's saying that all the portfolios that dominate all the sets of portfolios below, so if we're here, this one dominates. If we're here, below this one dominates. If we're here, this one dominates. So it's saying all of these that dominate all of these, this is the Markowitz efficient frontier. The hardest part of this question was breaking down what's being asked, saying, well, hang on a second, what are you talking about? Dominates all sets below the global minimum. So typically if you draw it out and just follow along with words, it's like, okay, I see what's going on. There we go. The dominant capital allocation line is the combination of the risk-free asset and the optimal risky portfolio, levered portfolio of risky assets, global minimum variance portfolio. Again, let's draw it out. There is our global minimum. This is our minimum variance curve. This is the efficient frontier. Here's our risk-free asset. And if we draw the capital allocation line, let's pretend it's tangent. This is the dominant capital allocation line, because remember, we can draw any capital allocation. The dominant one is the one with the highest slope that is tangent to the efficient frontier. So the dominant capital allocation line is the combination of the risk-free asset, and this is the optimal portfolio, right? And the optimal risky portfolio. Hey, we got it right away. Compared to the efficient frontier of risky assets, the dominant capital allocation line has higher rates of return for levels of risk greater than the optimal risky portfolio because of the investor's ability to, what are they saying here? Well, let's draw this out. There we go. There's our portfolio. And they're saying the dominant capital allocation line, this is it right here, has higher rates of return for levels of risk greater than the optimal risky portfolio. There's the optimal risky portfolio because of the investor's ability to, well, there's a higher return. There's a higher return. What is this called when we're on this part of the capital allocation line? We wouldn't want to be here. Why? Because for the same risk, we can get higher returns if we borrow. So because of the investor's ability to lend at the risk-free rate, borrow at the risk-free rate, or purchase the risk-free asset. Borrow. Remember, in between here, there's our lending portfolio. Anything out here is our borrowing portfolio. Leverage. With respect to the mean variance theory, the optimal portfolio is determined by each individual investor's risk-free rate, borrowing rate, or risk preference. Well, if we're talking about individual investors, there's no such thing as an individual investor's risk-free rate. It's everybody's risk-free rate. Individual investor's borrowing rate or risk preference. The optimal portfolio is determined by risk preference. Remember now, there's our capital allocation line. And you may have indifference curves with different levels of risk aversion. So this has got an A that's greater than the A here, which has got an A that's greater than the A here. Utility equals expected return minus 1/2 A, right? Measure of risk aversion. So it's the risk preference. The optimal portfolio is determined by the risk preference. So this person here would have a heavier weighting on the risk-free asset than the person with this indifference curve, which would have a higher weighting than this person, and on and on. There we go.